So as a 30-second recap, here is our flowchart for the index of loop. Go ahead and pause it and stare at it. What we do is we keep searching the string until we find the character that we want, starting at position 0 and going as long as the position is less than the max. But if we ever find it, found at becomes set to our current index position, and that makes this condition false, and we will fall through the end of the while loop and return our value. And here's the code to match. So you can pause that if you need to, and it will also be in the notes. And here's how we called it. It turns out that the string method, the string class already has an index of method. So practically speaking, we didn't have to code that, as is the case for a lot of the common things that you do. They've been coded in the past. If we wanted to do it with the string method, we would just do this. I is equal to s dot index of t. That's the shortcut for it. That searches the s string for the first occurrence of t. Or if you want to find the last occurrence of t, if you want to start at the end and search the other way, you can do I is equal to s dot last index of t. And there are variants of index of. The Java's index of function is more powerful than ours because it also supports searching for an entire string within the string. And ours isn't nearly that sophisticated. It'd have to be a more complicated loop. Because once you find the first character that matches, you would then have to keep going, to see if you'd found the second one or not. So it's more complicated. So index of also supports, come back, a version where you can specify a starting position. If you want to ignore the first 10 characters, then you start at index value 10, and it would go that way. So sometimes as you're processing, you want to find all of the i's in a string, or all the periods, or all the somethings. And so you might need to make use of the ability to start at a specific index.
Question about NetBeans in general.
Yeah.
So, it's got those pretty helpful Intellisense guides. When you come back to something, you may not, recognize what each of the kind of arguments for each function are.
Right.
Is there a way that NetBeans will redisplay that?
Right. So since, like if I wanted to do index of t starting at position 2, and I didn't remember what those were,
Right.
I could highlight that and hit F1 or right-click and do Show Java Doc. Oh, it's not F1, it's Alt F1. But anyways, right-click and do Show Java Doc. It's not going to pop them up in the little thing, but you'll see the entire documentation for the method.
I've been pressing F1 and not getting any.
I was thinking it was F1. It ought to be. Isn't that what it is in Visual Studio?
What it is in almost everything.
Yeah. Okay. So anyways, it should have done that. Okay. So let's make a better string. String is equal to rows state is really awesome. And we want to write a loop that will print out the index value of every E in it. So I think in this case I am going to make it a while true loop and use a break statement. So let's look for the first occurrence of an E. S is equal to, I need a variable to indicate the last time it was found. So I'm going to declare a new counter, and I can't think of a good thing to call it, so I'm just going to call it X because that's a really bad name for a variable. Maybe I'll call it last, but that makes it sound like the, okay, yeah. Here we go. So this is our starting position. We're going to start searching the string at position 0. So I is equal to s.index of, and we want to find every E. We want to find the first E, but starting at position 0. Nope, starting at position last. If I is less than 0, or if I is equal to -1, we didn't find a darn thing and we want to break. But if we did find something, good news. Now we can print that out, system.out.println E found at plus I. And then we can set our last position equal to I. Okay, so I'm going to go back and I'm going to make 2 changes to this. But whenever I go back and start editing stuff I've always typed, it leaves some people behind. So please to make a note, we're going to set last equal to -1, and I had a nagging feeling I was going to do that. Go make that change, please. Last is equal to -1. And then when we do index of, we're going to make it last plus 1. So we start at 0, but then if we find E at position 6, we're going to start searching the string at 7. And then if we find E at position 23, then we're going to keep searching from position 24. And just to make sure this works correctly, I'm going to stick in 2 E's into my string in a row, just because I want to make sure that it doesn't accidentally skip one of them. Nope, it found it at 3, 4, 10, 16, and 24. If you didn't add the double E on yours, your numbers will be different. Okay. So this is indicating a different way to use the while, but I know we've talked about using break before. Flowcharting it is a little bit unusual, or it makes language constructs like this are newer than flowcharting. You know, flowcharting has existed since before the invention of electronic computers. So if you were going to flowchart something with a break statement, and if I do this I'm going to tab off of it. Is everybody done typing? If not, that's okay. You doing okay? You got yours typed in? Okay, cool. So a loop with a break looks like this. Do some setup maybe, but what's most important is that you just put, and it doesn't have to be while true. You can break out, we could have broken out of our index of loop. We could have written that to use a break, and as a matter of fact, why don't I just copy our index of loop and then modify it to use a break statement. So my while condition can be simpler because I'm going to trust the break to get us out early. And then down here, after I have found it, I would issue a break. And to me, it ought to be in a different symbol than just a square, but I haven't ever found anybody indicate how that should be flowcharted. And so, when you hit a break, it looks like it ought to hook back up to there, but in reality, it goes all the way to there. And that's a nasty flowchart at this point. There. You see what I mean? As soon as we hit our break, we exited the while loop completely. And so it kind of breaks our rules of an if statement having 2 branches that hook back up together. But that's the way it works. Conceptually, it's really clear to see how it works. But then if you try to justify it with the rules of flowcharting, then it starts looking ugly. In my opinion. Maybe you think it's a work of art. I will hang it on my fridge. All right, we are actually done with Chapter 4. I don't see anything in there that we haven't covered already. So we're going to go to Chapter 5. Using pre-built methods. The string method has a lot of different methods. We've already used I know, char at. Have we done index of and substring? Well, I mean, obviously we just did index of. Have we done substring? I'm not seeing a lot of shaking head yeses. Okay. So API. application programming interface. When you write a complex system, what you're going to wind up doing is dividing your code up into classes, and in each class will have a set of functions, a set of methods that can be called by your program. Well, you can write up the documentation for that and publish it, internally for your company or whatever, and that is the application programming interface. That is how somebody works with your code. So if somebody else is going to borrow your code and modify it, or use it in order to do something, in an API, typically, or not typically, but could involve like a graphics library, draw something at X, Y, or it could be controlling a device. All of our APIs inside of Java that we're dealing with here are a little bit more mundane than that. We have a scanner class API, and so the scanner has methods like .next and .nextInt, next double. Those are the API, but I'm going to stop using API. Those are the methods of the scanner class. Then there's the math class. Math calculations are sometimes rather complicated. We don't want to have to write a sine or a cosine or a tangent formula ourselves. We could do so, but we don't want to have to do that. Just like we don't want to have to calculate pi ourselves. And again, there's an algorithm that calculates pi, but writing it is kind of nasty. We would just rather use pi that's built into the math library. So if you're going to use the math class, most classes that you bring in, you have to add an import for. I believe the math class in Java is an exception. I believe if we go to our code, and down here we type double D is equal to math.pow 10 to the power of 3. Yeah, I did not have to go up to the top and add an import. The math class is one of the few things that is brought into Java automatically just to make programming easier. And in some languages like C and Python, that's not true. You actually have to import math classes in order to get the power of them. So POW is a method that's inside the math class. It takes two values, one value being the value itself and the next one being the exponent. So this is 10 to the power of 3. There are other ones. There's the absolute value, math.abs. What's the absolute value of negative 10? Well, it's going to be 10. What's the absolute value of, what is 10 to the power of 3? It's 1,000. There are min and max functions. Math.min, which one of these values is smaller? 1 divided by 3 or 1 divided by 4? Let's make these 1.0 so they'll actually be doubles rather than floating points. 1 divided by 5. After we run this, which one should be smaller? Yeah, 1 divided by 5 is smaller than 1 divided by 3. So when I run this out, it should say 0.2. Then max works about the same way. D is equal to math.max, which is larger, 1 or 2. It's going to print 2, or it would if I tried to print it out. If we just type math and dot, we will see, as you were noting, all sorts of things. There are absolute value functions for doubles, floats, ints, and longs. So that kind of fluffs up the length of the list. Add exact, well, that's interesting. That's kind of implying that the rest of our addition isn't exact.
Yeah, I wonder what the basis of precision is then.
It returns the sum of its arguments, throwing an exception if the result overflows. I guess that's its key. Normally adding might not generate an exception. I guess we could find out. Let's add two numbers. Int b is equal to 2 billion, 1, 2, 3, 4, 5, 6, 7, 8, 9, plus 2 billion, 1, 2, 3, 4, 5, 6, 7, 8, 9. System.out.println b. Now there's no way that the compiler can know that this is not going to work. That would be expecting too much to know that that was going to be overflow, that we were going to exceed the capacity. And so it didn't flag that as being bad, and then when it ran, we got some garbage results. So that add exact would have generated an error, an exception to catch. B is equal to math dot add exact, and I could add those two numbers, 2 billion, 1, 2, 3, 4, 5, 6, 7, 8, 9, and another 2 billion. I should have stored that in a variable. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. That should actually blow up. So it blows up. So there is a reason for that function. What do you know? I hadn't noticed that before. Math dot pi is in there. D is equal to math dot pi. There's also E. There are log functions. Log base 10. Log base 1p. I'm not sure what that would be. I could learn so much just by looking at this. So natural logarithm of the argument and 1. Okay, anyways, all sorts of different math functions. Oh, floor and ceiling. The floor of 3.9 is 3. It rounds it down. Floor just means round it down if it's not a non-even number, kind of like the integers do. Ceiling means round up. If I could spell ceiling, it would have. There we go. So 3.9 rounded up would go to 4. Oh, it was just seal and not ceiling, excuse me.
Does that return an int, or does it keep it as a...
I'm sorry, pardon me?
Does it return an int, or does it keep it as a decimal?
Good question. Let's find out what it returns. D is equal to math dot ceiling. Why are you not popping it up? Okay. It's returning a double, interestingly enough. There's no reason for it to, in my opinion. And then there's a round function, which obeys the rule that if it's, 3.5 and above, it rounds up, and 3.49999 and below, it rounds down. So D is equal to math dot round. If we round that, it should be a 4. Let's run it and make sure. I'm always curious to find out whether a library rounds 3.5 up or down, so I'm going to run this 2 times. All right, rounding 3.6 did get a 4 as I expected. How about 3.5? That's a 4 as well. How about 3.49999? Okay. Wait.
What?
What?
Well, closing.
Huh. Apparently I just added too many 9s to it. Alt F1. Round. Returns the long closest to the argument with ties rounding to positive infinity. It doesn't really explain. Okay, anyways, like I said, I'm always curious to see how it handles things around. I wonder at which point it decides to round that one up. That'd be a question to ask Stack Overflow.
So what's
The number of 9s is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we have 16 and 17. What is the precision of a double in Java? How many characters does it support? So a double is 64 bytes, where 52 of them are used for the mantissa, which is the number that's not the exponent, and then 11 bits are used for the exponent, and then 1 bit is used for the sign. So anywhere between 15 and 17 decimal digits is supported in a double, and we're kind of up against that level. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We're asking it to do a calculation with 17 digits of precision, and that may be just a little bit too long, and so it went ahead and rounded it up before it did anything. What would happen if I stored that in a variable and then printed it out? Sorry to go off on this tangent. Maybe this is useful for y'all, or maybe you're playing Candy Crush. Let's go look. Yeah, check it out. Just when I declared that as a constant, it went ahead and rounded it up to 3.5 because I had exceeded the precision. So that makes sense.
You familiar with bankers rounding?
No.
It's what Microsoft Access does, even though Microsoft Excel doesn't.
Oh, yeah?
And so like 0.125 will be rounded to 0.12, whereas 0.135 will be rounded to 0.14.
No.
The
Why?
5 determines which way it's going to go up or down based on the number in front of it, odd or even.
That's
It's
bad.
Terribly obnoxious.
That's obnoxious.
It might be the reverse of that, but it's.
But yeah, I get the idea. That is crazy. So to use a method, you need to know what type of data to pass it, what arguments to pass into it, and then what it returns. All of these functions that we've used so far have accepted doubles and returned doubles. But they also can accept ints. But an int will be converted on a fly to a double, and that kind of conversion is acceptable when you're going from a lower precision, smaller format to a larger one. So you could pass an int to it, a long to it, a float to it, and it'll handle all of those, converting it to a double. So we don't really have to worry about whether we're feeding the math.floor function integers or floats or whatever. They all get upgraded, they all get promoted to doubles on the way in, and then a return of a double. So, to write our function, public means that it's accessible outside the class so that it could be used inside another class. And then that's the return type. And then you give the function a name, the method a name, and in between the parentheses you list the parameters. Here they're calling them arguments. The terms are very similar, but they have different meanings. Parameters are what they are called when you're inside the function, and arguments are the data that is passed to it. So if we go back to our index of code, here, S and T are parameters. The parameters are the variables that live within the scope of this function. Then the arguments, that is an argument, and that is an argument. Even though they happen to have the same name, they're conceptually different things, because the arguments could be constants. We could look for, the occurrence of the first O in wow or whatever. So the arguments fill the parameters. And the textbooks don't always make that distinction clear, and I sometimes fumble them when I'm talking about them. But if I'm saying it correctly, I'm calling it an argument when I'm looking at the function call, and I'm calling it a parameter when I'm inside editing the function. So the math class, ABS, absolute value. Max, there's another one. Here they wrote 2 versions of max. And the reason they did that is because sometimes you would want to get an int out of it, and sometimes you would want to get a double out of it. Now in my mind, you could just cast the result to an int if you wanted an int out of it, but they went ahead and provided 2 versions. Why would not one version be enough? Here I was bragging about how things will get converted to a double if that's what the parameter takes. Well, I'm not going to even explain. When we talk about method overloading, it will make sense. Okay, and then there's a minimum function, and then there's a power of function, and then there's the random. Random returns a number between 0 and 1.0, not including 1.0. Then you have to convert that. If you're going to use this random number generator, there are other ways of doing it in Java. You have to do something to convert it to the range that you want. So if you're mimicking a Yahtzee and you want to roll a 6-sided die, you would have to change this value so that it no longer was a range of 0 and 1 or 0 and 0.9999999, but 1 to 6. There's a better class for doing that. It's easier to use, so I'm not going to talk about that one too much. Then there's round. Oh, why did I forget square root? Probably because you could use the POW function to get the square root. These two things do the same thing. D is equal to math.pow. I want the square root of 2, so I'm going to raise 2 to the power of 0.5. That gets the square root of it. 2 to 1/2 is the square root. Then D is equal to math.sqrt2. That syntax is certainly cleaner. If you have a language that supports an exponent character, like if you could type this 2 to the power of 3 and actually have the language support it, then that's a sneaky quick way of getting square root without even knowing what the square root function is called, is to take 2 to the power of 1/2. Java doesn't have an exponent character. C, I believe, does not either. Python does. It's ***. That means 2 to the power of 1/2, which is the square root. So if you wanted to get the cube root of something, you math gurus may correct me, but the cube root of 2, I believe, could be calculated like this. Is that not correct? Take something to the power of 1/3. So let's see if that works. The cube root of 27 is 3. System.out.println D, just because I want to see. Hopefully that's 3 when it's done. Yeah, okay. Horton's law says that the length of a river is related to the area drained by the river. So if you know the square miles of a river that it covers, that it drains, you can supposedly calculate the length of it. That's interesting. It's to the power of 0.6. All right, I'm not seeing anything else in here that we really need to explain. The wrapper class. The wrapper class are the same versions, or excuse me, they're named similarly to the primitive data types, but they start with a capital letter. And if they don't think that it's a whole word, they go ahead and make it a whole word. So the wrapper class for char is character. The wrapper class for integer, for int, is integer. These give extra functionality that these do not have. In some languages, every data type is a class and comes with functions attached to it. C# is that way. However, in C++ and in Java, you have primitive data types, which are just numeric values. And then you have classes. And the classes give extra abilities, such as, say we have a string, 3.9, and we want to convert that to a double. Somebody has typed in 3.9, and we weren't lucky enough to have a scanner.next double in order to do the conversion for us, but we can do that conversion. D is equal to double dot, and double in that case was spelled with a capital D, parse double, parentheses, S. That attempts to do the conversion, and it throws an exception if there's something wrong with it, like if there was a letter in it. That could not be converted into a double because it's not a proper number. So this is an example of using the wrapper class. You could give values to elements in the wrapper class. We could say that, oh, by the way, that's a DD. I mean, that's a double. Usually you don't have to do that, but there are some data structures which require the data to be stored in them to be enclosed in wrapper classes rather than primitive data types. And if you take advanced Java, which I hope all of y'all do, then you'll come across that concept. I'm not sure we're going to hit it before then. Let's see what else the wrapper class supports. DD dot, suppose you have something stored in a double. Not too many of these are real interesting. I'm not seeing anything there. Okay, but double dot, we see all sorts of interesting things. The maximum value that a double can support. The minimum value that a double can support. The maximum exponent. The minimum exponent. We can find out all sorts of information by querying the double wrapper class. Size, I guess, would just be the number of ints. Since it's a 64-bit data type, I would hope that its size would return 8. Then there's these other things. Parse double. Turn it into a hex string. Just turn it into a plain string. Let's do that. Now that we have something stored in D, let's turn it into a plain string. S is equal to double dot I've already forgot what those are called. Two hex string and two string. Okay, so double dot two string and pass in the number D. That converts that converts our double back in to being a string, so that you could send it down the internet or into some API that required a string rather than a numeric value. There's a faster way, a cheaty way of converting something to a string. This does it as well. That's kind of goofy looking to non-Java programmers, but all this is saying is take an empty string and then concatenate it to whatever follows it. So D gets converted to a string, just like we've seen when we did our prints, you know, and you added something, you printed two strings, or you printed a string and then a number, it gets converted to another string. So that's a fast way of converting it to a string, and when I say fast, I mean in the shortest number of characters. It's not any faster for the computer. And here's the more proper way of doing it. And I really just do that all the time, because once you see that and get used to it, yeah. But that looks better. Okay, so S is equal to double dot two hex string. I'll be real curious to see what the hex string for 0.33 is. So I'm going to print that out. Huh, what do you know? Check that out. There's a P there. I've never done this before. I've never tried to get a hexadecimal string of a double. But I know that that P has to mean...
E, when you're base 10, is it an E there?
Yeah, so it would be an E if it's base 10, so P if it's an exponent in base 16.
Yes, E could be an actual digit.
So that's interesting. Let's do another value, like just 333. Now I'm going to do them both. These should be the same except for the exponent, but that's in base 10. In base 16 they may look completely different. Yeah. Wow, that went from a P of -2 to a P of +8. That confuses me completely. I'll have to find out what that does. Alright guys, let's stop our lecture here. And if y'all would be so kind as to do these Instructor Evaluation, but I'm going to have to ask for a teacher's pet to take it downstairs and slip it under the door of the office. So, who knows where the office is and is willing to do that once class is over? I'm going to
Which
pick
office?
someone. Pardon me?
Which office?
Just someone downstairs.
Okay.
Alrighty.
But I don't know where the office is.
Yeah, the office is the where the secretaries and the admin people sit down there. So, my name is Jeffrey Thompson. This is CIT 1613, Intro to Java. Our class number is 7684, and the rest of it you can figure out because you know what year and semester this is.
Wow, that's a lot of responsibility.
All right, and I brought pencils. Anybody needs one? So the way this works is you just fill it out and then you say good things about me, so I'll give a raise.
Obviously.
No, I'm kidding.
There you go.
Give me an honest
Oh, does it need to
evaluation.
be a pencil?
Yes.
All right, I actually have a pencil too, so we're good. Wait. No, that's a tire pressure gauge, thank you.
You're trying to write it out.
I don't think it worked very well.
And I'm not allowed to be in here while you're doing that in case I unfairly intimidate you or something like that. So I will step out into the hall. And this is it. Once you do that, then class is over and I will see you all on Tuesday.
Fantastic, have a good weekend.
Oh, you too. All right, guys, so one of the things we did last time is do loops that would calculate, I believe, the factorial and the summation. We're going to flowchart those loops. We're going to do one as a do loop and one as a while loop. So just as a reminder, let's write a little summation loop. I should ask that as a quiz, but I'm not going to. So to do a summation, we have to have a sum variable. We have to initialize it to 0. And we're going to do this with a while loop. We could easily do it with a for loop as well. Since it's a while loop, we need a counter. We're going to start it off with, I guess, 1. And then we need an upper bound. So I'm going to set max equal to 100. Then we have while. While I is less than or equal to max, we add that onto the sum. Sum plus equals I. And then we increment I. So that's our summation loop using a while loop. Let's do a factorial loop using a do loop or a do while loop. Same kind of idea. Instead of calling it sum, let's call it product. Then we're still going to start I off at 1. We're still going to need a max. And then do, the product is equal to the product times I, add 1 to I, and keep doing that as long or while I is less than or equal to max. Alrighty. So we can draw those pretty easily. Squeeze that over there. I'm using a program called Lucidchart. Those of y'all who've had 1113 with me have used it before. So I'm just going to include 3 of those things, these 3 statements, in one process block. So sum is equal to 0. I, and a process block is where math occurs or other simple action. I is equal to 1. Max is equal to 100. Then we have a decision. The same symbol is used for both ifs and whiles. While I is less than or equal to max, and we don't have to put it in quotes when you're doing a flowchart, but or in parentheses, however we will, just to make it match our code. Then come over here and do the body of our loop. What's the first line of code in our loop?
Plus or equal to I.
Yeah, sum is plus equal to I. And then we have one below that. That's the I plus plus. And I'm putting those in different blocks now for a reason, and I'll show you why. Then when it's done, it has to loop back up to the while loop. An if statement doesn't go back up. Instead, it splits and then they join back together and they keep going down. But a while loop is going to keep going over and over and over until it's done, until this condition is no longer true. So then we're going to just, after that we're going to, maybe print it out or something. Print result. So C out the sum, which I didn't actually have over here, so I'll add it. C out the sum. So that's our summation loop. The factorial loop is going to look so similar that I am not going to redraw the whole thing. I'm going to take bits and pieces of this. How is this similar? Well, we do something kind of similar here. We do something kind of similar here. So I can grab that block, put it down here, except we start our product and we start it equal to 1. Then we do these two things, except one of them will involve the product rather than the sum. So product times equals 1, or I. Then we have our decision. Keep repeating this while I is less than or equal to max. If I is less than or equal to max, we want to come back up here and do this again. Flowcharts can get annoying. Whatever. You get the idea. And then when it's no longer true, we will print our result out. That's good enough. Alrighty, so those are our two loops. Let's bring them up side by side for a moment and compare them. So I hope you see the difference between a do loop and a while loop. Which one is post-test and which one is pre-test? Yeah, this one is pre-test. The test happens before the body of the code. This one is post-test because it happens after the statements are done. So you know that this stuff's going to happen at least one time. Whereas it's possible if I was set incorrectly, it wouldn't do any of this at all. In which case, sum would still equal 0. Grab that code, paste it in over here. Okay. The fact that I'm spending so much time on these probably implies that I want you to memorize these guys. So I know, or at least I'm pretty sure that we had a homework assignment based on writing a little bit of a summation loop and a factorial loop, but make sure you burn it into your brain. It's really not that complicated, is it? I'm not going to ask you to draw a picture of it. But really, it's only 1, 2, 3, 4, 5, 6, 7 lines of code. Some C programmers like to get fancy and combine things into the same statement, in which case you could shorten this. You could do that at the same time. That means add I to some and then increase I. Is there any benefit to be gained by writing it like that? Not in my opinion. So I don't do that. So, are we not done with this chapter, actually? To test to see if a number is in a range, you use AND. I want to make sure that my number is between 0 and 100. So, if grade is greater than or equal to 0 and grade is less than or equal to 100, then print it's a valid grade. Or you can see if a grade falls outside of a range or anything is outside of a range. And to do that, use an OR. If the grade is less than a value, it's invalid. Or if a grade is greater than invalid. So if you're going to do that using my classic example of water temperatures, you could do if temperature is greater than 32 and temperature is less than 212, you'd say liquid because it's neither frozen nor boiling. Or you could say if temperature is less than 32 or temperature greater than 212, you could do not liquid. The conditional operator is that weirdo guy where you have the question mark, and if this thing is true, then whatever before the colon happens. And then if this thing is false, then whatever after the colon happens. We talked about the switch statement. We talked about the break statement. We've seen break statement in 2 different places, I believe. We've seen it in loops, right? And we've also seen it in the switch. So we are done with this. Chapter 4 is at an end. So I need to make a Chapter 4 review. I will do that and try to have it posted by tomorrow. But I'm not going to make it due super soon. The sooner you got it done, of course, the sooner I could grade it. And by super soon, since we have fall break next week, then I'm just going to make it due the following Monday. Feels low energy in here to me. Is it just me? All right, loops and files. I guess I went ahead and did all the loops before we even hit the chapter. That'll make this a really fast chapter.
I'm not sure if you went over all the loops in here.
Did I not? Are do loops?
I know what they are, but I don't know if you went over them in here.
Did I lecture on do loops?
Not
You nod yes or no.
I thought so. I don't know.
You thought so?
maybe. We went over it like once.
Once. Well, we can cover it once more real quickly. Well, we'll find it again in this, so that'll work. I don't mind if y'all see something twice. Burns it in. That's also why I don't mind kind of running off far afield in my examples and then coming back to it and hitting slides on it. So plus plus means to add 1 to the operator, to the value. So if I do I plus plus, it means add 1 to I. But there are 2 versions of it. If the plus plus comes before the variable, it means something a little bit different than if it comes after the variable. And you Python programmers have not seen that before. You've seen this. You've seen I plus equals 1, because Python doesn't have plus plus. This means, what? Oh, okay. This means the same thing as that. It's functionally equivalent. If I type this, I is equal to 3, and then I type Cout I plus plus, like that, it may not print what you expect it to print. Well, I don't know what you expect it to print, but what it's going to print is a 3. But by the time it's done, I is equal to 4. So what happens is it comes along here, it prints I, then it adds 1 to it. So the plus plus happens after the entire line is executed. So effectively, by the time we hit the semicolon or whatever. So this prints out the value of I before it gets modified, because the plus plus is the last thing to happen in that expression. But if you use plus plus the other way in front, let's do that again, just set I equal to the same value. And you print out plus plus I, it prints a 4. And when it's done, I is equal to 4. Is that super duper important? Well, most of the time it's not. Because if you're writing some kind of loop like this, while x is less than 10, blah, 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 x plus plus is on a line all by its lonesome, it doesn't matter whether you put the plus plus in front of the x or after it. Why? Because you're not using its value inside of the statement like we were here. It's happening on a line all by its lonesome, so it really didn't matter in which order it happened. But it's when you mix it up in another expression that the order of it becomes very important. So if you did this, x is equal to 10, y is equal to x plus plus times 2. What do you think y equals at this point? It equals, okay, I shouldn't say that. What does it print?
It'll say 20. I don't know.
You're correct. It will say 20 because x equaled 10 going in here. The plus plus doesn't happen until the rest of the line is done, so 10 times 2 is 20. So it's going to, so y at this point prints 20. And then if we printed x, of course, x is now equal to 1 more than it was. But if we do the same thing, x is equal to 10, y is equal to plus plus x times 2, and then we print out y and we print out x. I know I misspelled that, I'll come back to it. Now what is it? Yeah, because the addition, the increment happens first, before anything else does. It's the very first thing that happens in this expression. So x turns into 11, then we multiply it by 2. So it'll print out 22, and then x still winds up being the same value of 11. Where's my cursor? There it is.
But if x plus plus times 2 is on its own line, why would it not print out,
If it was on its own line,
like it's shown, y equals x plus plus times 2? You're saying that equals 20?
what's happening is the order in which the increment is dependent upon whether it's before or after. Let me copy these statements and then rewrite them in a way that makes them clear. This statement here is the same as writing x plus plus, oh nope, excuse me, y is equal to x times 2 semicolon x plus plus. But this statement here is the same as writing x plus plus semicolon y is equal to x times 2, like that.
So whenever you have a plus plus, that's going to happen at the very end?
If it follows the variable, it happens at the end. Right. Just like that. And if it precedes it, then it happens at the very beginning before anything else happens in that line. Okay. Yeah, it's weird, isn't it? Just a little bit weird. So if it comes before the variable, it's called prefix. If it comes after the variable, it's called postfix. If you do it on a line all by its lonesome, it doesn't matter whether you use prefix or postfix. Most people do postfix just because of the way it looks. C++ rather than plus C. Minus minus works the exact same way, decrement. It's also got a prefix version and a postfix version, and it follows the same rules. So I'm not going to spend the time. Well, I guess I'll type it up. But, okay. So x is equal to 3. Y is equal to x minus minus times 4. What's y equal to? It's equal to 12 because the subtraction, the decrement, happens after the multiplication. But if we do it the other way, x is equal to 3 minus minus y times 4, then what's y equal to? This happens first, so it becomes 2 times 4, which is 8. Very good, y'all. Okay. Introduction to loops. The while loop. The way the loop is written is you have the word while followed by an expression inside parentheses, a condition, and then you have a statement. If it's a single statement, you don't need braces. If you have more than one statement, you do need braces. It's not a bad idea to go ahead and put braces on it even if it's just a single statement, just because that makes it easier to come in and add something later. So the expression is evaluated. If it's true, then the statement is executed. If it's not true, then nothing happens. That's like our flowchart over here. I have a more basic version up at the very top. Here's a while loop. While condition, they're calling it expression in the book. If it's true, then do something. Then come back up here and check again. Come back up here and check again. That's a while loop. It's called a pre-test loop. The post-test loop, oh, that's just another way of drawing it. While condition is true, do something, and then come back up here. Come back up here. I like drawing it like this because this indicates that when you went to the right, you started indenting your code. That's the only reason I do it that way. A do loop looks a little bit different. It's got the word do up here at the top, which you don't see at a flowchart. And then it does its processing and its update, and then the condition comes at the end. So it's a post-test loop, meaning that it does all of this stuff and then it checks. So you know that these statements will happen at least once because there's no way around those. Whereas in a while loop, these two are optional. If this condition isn't true to begin with, these things will never happen. So to make a decision on whether you want to write something as a do loop or a while loop, you have to think to yourself, is the code that's inside the loop something that always has to happen, or if it's okay for it to be skipped? If it's okay for it to be skipped, then you could write it as a while loop. If it's not okay for it to be skipped, if for the code to work correctly it has to do this at least once, then you make it a while loop. Yes, thank you. You make it a do loop. I hate the fact that the word while is, there in both of them. So the code for both of those is pretty similar, but you could do something like this. Int x is equal to 0. Int, now I'm going to make double sum. I'm going to make it, I don't even know what I'm going to do. Simplest loop possible. While x is less than or equal to 100, print x and then add 1 to it. That's the simplest while loop. It's pre-test. If for some reason x was set to 1,000, it wouldn't print anything. because x is not less than or equal to 100. That's like an if statement. It skips these lines. Now we're going to write it as a do loop. Int y is equal to 0 while y is less than or equal to 100. Print out y. Increment y. But I meant to make it a do loop, so there. I put that word there. I make that there. And this is the only time you put a semicolon after a while statement is when you're writing a do loop. And it's just so that it knows when it ends. If you stuck a semicolon here, it totally breaks the loop. I'll go into that more just a little bit. So this is a post-test loop. So even if this was set to a weird value, like 10,000, it's still going to print out y at least one time. Because it comes in here, it prints it out, it adds 1 to it. Well, now y is equal to 10,001. That's certainly not less than 100 anymore, so it's done at that point. But if you set it, equal to a reasonable value, they both behave exactly the same way, logically or functionally. So your rules for using loops. If the body of the loop needs to happen at least one time, use a do loop. Then there's the for statement. The for statement has the initialization. Okay, if we were going to put comments on this, this is an initialization. Here, I'll just copy this again. This is where you initialize. This is your condition. And this is your update. A for statement has all three of those things right in the header. For, where you initialize it, your condition, and then your update, and then you put something in the body, right there, the body of the loop. So to rewrite this loop as a while loop, as a for loop, for int x is equal to 0, x is less than or equal to 100, x plus plus, cout x. I like for loops because you don't forget to add the x plus plus like I always do when I'm writing a while loop. I've managed to catch most of that for y'all, but I haven't done it every time. So I don't know which one of these you like better. I like that one better. It makes it instantly clear what the loop is doing. You don't have to go and search through the code to find out how x is being incremented, whether 1 is being added to it or 10s are being added to it or whatever. Just at a single glance the entire behavior of the loop, barring any instances of break statements in there. Pretest just means that the test happens before the body of the code. Watch out for infinite loops. The loop has to have code that makes the condition, the expression, become false, or else it never leaves. If this condition here never became false, it would endlessly loop. So this update had better perform some kind of change that'll make this condition eventually become false. Like if we're adding 1 to x, and this is x is less than or equal to 100, eventually this condition will no longer be true, so it can exit. But if I forgot the x plus plus, if I forgot the update statement, or I did some kind of update that didn't actually change anything that the while was checking for, then it would be an infinite loop. And the only way out of that is if you add a break statement. You can use a break statement to do an early termination of a loop. And that looks something like this. While, let's set I for x is equal to 0 again. While x is less than or equal to 100, we're going to print x. But if x ever becomes larger than 50, we're going to break. Or let's just do if x is equal to 50, break. And then print done. For heck, let's print x again. So the final value of x will be what? Well, x starts off at 0. We print it out. We print 0, it's less than 50. If we print out 1, we print out 2, we print out 3, all the way up to the point where we get x is equal to 49. We print 49. 49 is not equal to 50, so it doesn't break. We add 1 to x. It comes back up here. Is it still less than 100? It sure is. But right now it's 50. We print out a 50, but then there's a sneaky if statement. If x is equal to 50, that is true. And so break means, nope, we're going to exit the loop early. And so we come down here. And so this would print out 50. Are you really going to write a lot of loops like that? Probably not. You probably don't need to exit loops early. The only time I tend to use break statements is when I do a while true loop. And a while true loop is good for when you're doing some kind of input. Like if you want to force somebody to enter some good data. X is equal to 0. You tell them, okay, while true. You say, enter a value less than 10. Then we read that in. And if x actually meets our case, if x is actually less than 10, we're going to break. Else we're going to print an error. Error must be 10. So this is kind of like a trap from which the code will not escape until they finally type in a valid value of x. So we're using this for data validation, for input validation. We've also used while true loops to do that kind of thing where we say enter a number or -1 to exit. You know, if x is equal to -1, then break, else do something with that data. It's the same idea. Otherwise, this would be an infinite loop because the expression would always be true. But the break gives us a way out of it. There's also a continue statement. Let me show you what that one looks like, if I can think of a way. No, I'm going to skip it for now. Maybe the slides will show us. So, an infinite loop is one in which the expression, the condition, eventually becomes false. If it never becomes false, the code has no way of stopping unless there's a break statement in there. Here's an example. Number is equal to 1. While number is less than or equal to 5, print hello. Nothing ever changes number, so it's going to loop endlessly. Using while for input validation. I just showed that. They're showing a slightly different way of it. They're showing a way that does not use a break statement. But to do that, to do it without a break statement, but to do it with a while rather than a do, requires us to have what's known as a priming read. We have to read the data once before we check to see if it's invalid. If it's invalid, we display an error message and then we read the input again. So it actually takes 2 input statements in order for us to get this to work if we're going to do it without a break statement. And that looks like this. Here's our code that asks for that number less than 10. We're going to rewrite that. X is equal to 0. We're going to see out, enter a value less than 10. We're going to ask them, or we're going to let them type it in, and then we're going to do this. While x is greater than or equal to 10, they typed in something wrong, we're going to display an error message. Error must be less than 10. So far, so good. So far, the code is about the same. But if that's all we had, it would display that message endlessly. We have to then tell them the rules of the game again. Enter value less than 10. Maybe they could get the idea from the error message, but maybe not. And then we have to read that back into X again. So that's doing it without a break statement. Maybe it looks cleaner because there's no break statement, you know. It's just whichever way your brain works. However, I have a strong bias towards doing it this way. And the reason for that is I don't like having to repeat the code. I don't like seeing this C out and this CIN statement both here and here. And why is that? Well, because the code for getting the input might be complicated. You know, it might not just be a one or two statements. There might be a considerable buildup, you know, required in order to get your input. So I'd rather only do it once in the code. But this is how they typically, how the textbooks always show how to do input validation. So this is input validation as per the textbook using a priming read. And why is it called a priming read? It's like priming the pump. If you push the pump and no liquid comes out, you have to start doing it over and over and over. You know? So you have to prime your value with a single read first, and then if it's incorrect, you loop on it until it is correct. I hope the difference between these two loops is apparent. Input validation as per the prof. No priming read necessary, but uses a break. Here's their example. Wow, what do you know? It's exactly the same example. The only difference is that they made their error message include both the error and then the entry message again. Same idea. Enter a number less than 10, let them type it in. While the number is greater than or equal to 10, continue to loop until they finally give in and type a good answer. Here's the flowchart for input validation. Read the value. That's our priming read. Is it correct? Yeah, display an error. No, it's not correct. Display an error message, read another one, and then keep looping. Counters. A counter is your variable that's incremented or decremented each time a loop repeats. It can also be known as the loop control variable. So when we have our counter like this, when we're going x is equal from 0 to 100, x is our loop control variable. The do-while loop. Do something while expression or condition. This could be an entire block of code, of course, and that's usually what you see. And since it's post-test, that decision happens after the body of the code. Do while loop notes. Execution always happens at least once. The for loop. The for loop is the one that I like the most because you have the most information up in the header of the for statement. You have an initialization, you have a test, and you have an update. It performs the initialization, it performs the test. It does not immediately do the update. The update happens after the closing brace, really. Then it performs the statement, then the update is done, and the condition is checked again. So it is a pre-test loop. For count is 1, for count is less than or equal to 5, count plus plus, print hello. So how many times is it going to print hello? I think it's going to do it 5 times. It'll print it once, 1, 2, 3, 4, 5. Because when counter is equal to 5, it still prints it. What if we change this to 0 and less than 5 rather than less than or equal? How many times will it print?
None.
No, it's still valid because counter is less than 5.
Oh.
Yeah, 5. This is another way of writing a loop that goes 5 times. But if I made it 5, if I made it less than or equal to 5, that's deceptive because it actually goes 6. So if you're going to use less than as opposed to less than or equal to, you just have to make sure that you're choosing the right values. Because if I did that, it would actually print 6 times, although it doesn't look like it would. But you can add them up on your fingers and make sure. 0, 1, 2, 3, 4, 5. So it would print 6 times. For number is equal to minimum number, while number is less than or equal to max number. Add 1 to the number and then print that number out. or no, print that number times a number. I guess we're making some kind of a chart of numbers, and then there's squares. So we may as well do this. Let's get this one going. We'll print out numbers, their squares, and then their cubes. So let's start Visual Studio. File, new project. And let's make it a little bit more interesting. Rather than hard coding the minimum and the maximum, we'll ask the user for those. Choose empty project. Let's call the program squares. Right click on source files, do new, add new item. We want a C++ file. Alrighty, good old boilerplate. Unsigned include, IOStream. I don't think we're going to use strings, but I'm going to include them anyways. Using namespace std int, or void, yeah. Int main. System pause. Return 0. Okay, now we're ready. Let's ask the user for the minimum and the maximum. Enter the minimum and maximum. Separated by spaces. Separated by a space. Now I'm breaking this up into two statements just because it scrolled off the screen. You don't need to do that. Now we need two variables to hold, our minimum and our max. So I'm going to do min int min and int max, or just int min comma max, and let's read into it. CIN into min, I put my arrows going the wrong way as I am prone to do, and into max. We're reading two values in since we're letting them type in the minimum and the maximum. Maybe I should have done two print statements and then two CIN statements. That'd be more what you're used to looking at. But this is going to work as well. Now we need our for statement. We need a counter. I always tell you not to use single letter variable names in production code, but for counters it's so tempting. If you say for I is equal to 0 or whatever, or x, you know, I and x are canonical counter names. People use them all the time, so I'm going to run with it. So I is equal to min. For int I is equal to min, semicolon. Keep running while I is less than or equal to max. And every update do I++. And let's see out. I'm going to take a peek at their code just to make sure I don't do this wrong. Nope. Okay. C out I, followed by a couple of tabs, /t/t.
That's just tabbing over.
That just, yeah, it's like hitting the tab key twice. And then we're going to print out I times I, and then an end of line. And we don't even need to add the I++ like we would on a while loop, because it's already contained in our for loop. So enter the minimum and the maximum separated by space. I want to go from 10 to 20, and there it goes. It prints all the squares of the numbers from 10 to 20. Let's add another column for the cubes. So I'm going to need to print out 2 more tabs. So where it says ENDL, I'm just going to kind of hit return before that point and do another pair of tabs, /T/T, followed by an inside parentheses. I'm going to put I times I times I, so we will cube it. There we go. Now run from 1 to 15. And the output looks good to me. We could rewrite this loop with a while loop or a do loop. It would work just as well. Anything you express with one loop can probably be done with another, especially for and while. They are completely interchangeable. It's just that the syntax for one is different than the other. The syntax for the for loop is more concise, more precise. You can see it all, in one line. The do loop is functionally a little bit different, but you could still jigger your while loop in such a way as to accomplish it if you really, really wanted to. If you had a language that did not support a do loop, such as Python, then you can go through some hoops in order to get a while loop to behave like a do loop. That would consist probably of using a while true loop and then putting a break statement at the bottom in order to let it escape after the body of the code was done. You can leave any part of the for loop header out if you want to. And I'll give you an example of that. I'm going to rewrite this loop and make it look dumb. For int I is equal to minimum, and then I'm just going to put 2 semicolons. I'm not going to fill in those parts. Now it's going to look a lot like a while loop when I'm done with it. And I'll show you what I mean. I'm not making this body complicated. If I is greater than max, then break. Let's do the I++ first. I++. And then if I is greater than max, break. Now, would you ever code it like this? Not really. This is kind of brain dead because we have taken the advantage of the for loop and rendered that advantage useless by taking the update and the condition out of here. Now our condition is down here. We'll break out of it only once I becomes greater than max, and we put our update here. Is there any reason why you would code it like this? No, not really. But there may be times when you don't have any initialization step. Maybe I already has been set to the minimum before you got inside the loop, in which case you could leave that off. Don't type this, but what if I had done this? I is equal to min right here, or somewhere up above. Then I could conceivably leave that part off. But I didn't, so.
Would you still have to have that semicolon?
Yes, you have to have the semicolon so that it knows the pieces of it.
Oh, okay.
The first piece always has to be initialization. The middle one always has to be the condition. So I'm just showing this to you to let you know that it's optional. Actually, all 3 of them could be left out, in which case it looks extraordinarily dumb. There we go. You just do that if you want to frustrate somebody, I guess. Isn't that like the emoticon for crying or something people do? You know, the little tears coming out of the eyes. I don't know. So the parts are optional, but almost all the time you'll actually fill them in. So, when do you use the loops? Well, the for loop, always jump to the for loop in your mind first to see if it's appropriate. And it is appropriate anytime that you know you're going to have a counter. If something involves an initialization and a false condition that stops the loop and an update to occur at the end of each iteration, well, these meet the criteria for any loop pretty much. But if you know you're counting through a range, that's the perfect use for for loop. So we're going to make our little rules about when to use loops. When to use a for loop, when you will be iterating, counting through a range of values. So you know the range of values you will be going through. And when I say you do, the program will know by the point it gets there. I didn't know in my square program before I ran it what the range of values was going to be, what they would enter as their minimum and their maximum. But the code did. By the time it got to the for loop, it knew what the minimum and the maximum were. So that's when you use a for loop. And then when to use a do loop. When the body of the code has to happen at least once. And then otherwise, use a while loop. Really, I almost always use for loops and while loops. My brain doesn't think in terms of do loops, and not all programming languages support them anyways. So whenever you are tasked with writing a loop, think first if it can be a for loop. Now, these times when we do enter a value or -1 to exit, that's not a good use for a for loop. Why? Because we have no idea how many times it's going to repeat. We don't have a counter in that. I mean, we could add a counter, how many times that they said yes, but we're not limiting them to a certain number of times of repeating the program. So if we're doing what's known as a user query loop or a sentinel value loop, where we ask the user, do you wish to continue, yes, no, or we say enter a value or -1 to exit, that's not when to use a for loop. It'd be far better to use a while loop or a do loop for that. And that's actually a kind of time when a do loop would be fairly appropriate. Okay, so we know that loops are pretest loops. For loops and while loops are both pretest. Let's add that to our notes. And this will be the last thing we do today. Do loops are post-test. And you know what that means. Post-test means that the body of the code happens before the test occurs. The reason we're quitting early is we're going to hand out Instructor Evaluation. So let's make a Dropbox for what we've done so far. All right, there's a Dropbox there called Loops.